Okay, so in this lesson, we're going to go over bioenergy. So this is just kind of a broad overview of some of the different types of bioenergy. So you should be able to, by the time you're done, you should be able to define biomass, differentiate between all these different types of bioenergy sources, including between ethanol and biodiesel, and also be able to analyze and sort of understand some of the sustainability implications of biomass. So let's start at the beginning here. What is biomass? This was in your reading. So biomass is just material derived from living or recently living biological organisms. So I want you to take a second and see if you can think of a few examples of biomass. Go ahead and press pause and see if you can write down 2 to 3. And so here's some examples. Anything that's either currently living or has recently living. So, of course, wood is considered biomass. This is meant to depict algae. You have algae as a source of biomass. It's kind of a minor one. You can have straw, hay, whatever. Corn, as most of you probably know, is a really big one in the U.S. in particular. Manure, right? So manure is derived from a recently living or currently living organism, so a horse or cow or whatever. Manure is actually a major source of bioenergy across the world, including in the United States, and we'll go over one way that you can use it in the U.S. But you can, there is energy in manure. This is actually a picture of rapeseed, which is what canola oil is derived from. So anything that's, living or recently living, or came from a living organism is considered biomass. Now, it's important to point out that if you recall, coal, oil, and natural gas were all derived from living organisms, but that's where, they were not recently living organisms, okay? So coal, oil, and natural gas are derived from formerly living biological organisms, but they were not recently living, so they're not considered biomass. All right, so let's just take a look. I think this is surprising to a lot of people, but biomass is actually a major source of renewable energy in the United States. So this is a chart of the United States. You've seen this before. Primary sources on the left, end use sectors on the right, and then these lines indicate where each of these energy sources is going. And of course, this is in quads, which is quadrillion BTUs. Okay, so if you look at our renewable energy sources, we have biomass, geothermal, wind, hydro, and solar. So if you notice, biomass at 4.78 quads, bigger than geothermal, bigger than wind, despite the fact that you hear about wind a lot, bigger than solar. So it's actually the largest source of renewable energy. And just a quick note, if you follow the path where biomass is going, you have a little tiny bit that's going to electricity generation, only 0.5 quads. Thicker line. Okay, so we have a pretty decent chunk that's going to transportation, which you probably know. That's going to be your ethanol primarily. A little bit goes to residential, not very much. So that, maybe wood for heating, pellet stoves, that sort of thing. Commercial uses a little bit. Most of it's actually industrial. So there are some industrial processes that use biomass. So to give you another perspective here, so if you look, this is from 1949 to 2015. This is EIA data. So this is just renewable energy, and this is the supply of renewable energy since 1949. Okay, this is the most recent data. So feel free to take a minute and look at this, but you can see we have hydroelectric in black, we have wind in red, solar in, I guess that's a bluish purple, and then biomass in green. So what probably jumps out to you is, I would think at least two things. One, biomass is now the biggest source of renewable energy in the US. So this, corroborates what we just saw. But secondly, you can see right around this time, 2002, 2003, biomass took a huge leap in the US. Okay, it was always used, but huge leap in 2003. And if basically what happened around that time is when they started mandating ethanol be put in gasoline. So that's the primary reason that it jumped so much. But what I think is interesting to point out is that you hear in the renewable energy field, you usually hear mostly about wind and solar. Those are the two big sort of sexy renewable energy sources. And you can see they are increasing significantly since the mid 2000s. Um, but biomass is far and away the largest source of renewable energy in the US. Of course, if you look at bigger picture, so renewable energy as a portion of all of the energy in the US, and this was borne out by the previous chart as well. But so here's this green line is all renewable energy. So combine all of these sources into one line, and it's here, fossil fuels all the way up here. So just, it's nice that we're increasing, especially recently, we're nice that we're using it, but we have a long way to go before renewable energy makes a big dent in the overall energy mix in the US. And here, I'll show you two more charts just to show you different ways to look at it. So this is the overall renewable energy supply in the United States, and this just breaks it down by type. This is just to grant you a little perspective. You can see biomass takes the biggest chunk, and then here's a different way of looking at the same data. So this is based on a 0 to 100%. So since 2008, if you take 100% of all the renewable energy, this breaks it down into percentages basically. So you have, in this case, here's wood, liquid, and other biomass. And I wanted to point this out because this kind of, biomass is nice to look at because you can basically look at the top of this line, and this will sort of show you the trend through time in terms of percent of renewable energy in the US. And so the most current data, I believe, are from 2014. So if you follow it over here, we're at about right around 50% of all renewable energy in the US is actually biomass, which I think is surprising to a lot of people because you don't hear much about it. And then you can see the trend here is that it's projected to kind of decrease over time, whereas wind is, the line is getting thicker here, and then with solar it's getting thicker. Okay, so that just gives you a little perspective. Now to go over the types of biomass that are used. So this kind of breaks it down into which types of biomass are being used. So of all of the biomass used in the United States, about 45% is basically from wood or wood-derived fuels, so waste wood, pellet stoves, burning logs, that sort of thing. And then about 44% is from biofuels. Okay, so most of that is ethanol, corn ethanol that's put in gasoline. And then right around 10% is from municipal solid waste, and we'll go over what that means in a minute. So that's just to give you an idea of the different sort of breakdowns of each form of biomass that's being used in the United States. Okay, so before we get into the specific types of biomass, and this was in your reading, in order to utilize biomass, in order to, extract the energy or get the energy out of the biomass, there's a number of different ways to actually pull the energy out. So, as I'm sure biomass is, it's basically potential energy, right? So you have this, whether it's wood or corn or algae or whatever it is, it's not generating any energy while it's sort of sitting there. You have to extract the energy out of it, and there's a number of different ways to do that. I'm not going to go over all this chart. It goes way beyond the scope of what we need to learn, but I did want to go over a couple of key things here. So first of all, some terminology. You see two terms here: lignocellulose and then sugars and starches. Okay, so lignocellulose is just a fancy way of saying basically woody, woody biomass. So everything from trees to the stems of plants to even corn stalks. So there's the sort of harder part of the biomass, where sugars and starches are just think of it as food. So whether it's an ear of corn or a sugar beet or whatever, that's your sugars and starches. Okay, so it's important to differentiate between these because they actually require different means of extracting the energy out of them. And so just briefly to go over a couple of these things. Sorry, taking a quick step back. So lignocellulose, you can sort of imagine, it's very hard to break down. You just imagine, a piece of wood or even a corn stalk. I mean, that's pretty sturdy. Basically, it's pretty difficult to break down, whereas you have, something that's a food crop. It's not as sort of, hard, and it's a little easier to dissolve. Just imagine trying to, eat a corn stalk. that's kind of a good analogy. Your stomach has trouble breaking it down, whereas you can actually digest, some corn. So it's very similar in terms of actually sort of pulling it apart and getting the energy out of it. Um, and this is, kind of a bigger issue. They're really trying to figure out ways to process the lignocellulose, because it's otherwise not necessarily used as much as, obviously the food crops. Okay, so some basic, what these fancy words mean. Thermal conversion. Okay, so this is, the type of, energy extraction. This just means you're burning it, right? So combustion. Thermochemical. So thermo is heat, chemical is chemicals. So that's using heat and chemicals combined to extract the energy out of it. Biochemical conversion. So bio meaning, life or living organisms. So that's, using organisms, basically bacteria or enzymes, which is misspelled, to break down the biomass and sort of break it down so you can extract the energy. And then you have chemical conversion, which obviously uses chemicals. I'm not going to go over all the different types, highlight just a couple, because we'll address these in this lesson. But combustion, that's just burning, burning stuff. We'll go over that. You can imagine, you using a fireplace. I mean, that's taking, your woody biomass, and then you're combusting it, and then you're extracting the heat out of it. So that's a very simple example of a thermal conversion biomass source. And then biochemical, this is where we get our ethanol. So we'll go over a little bit about corn ethanol, but that's actually a process called fermentation. You don't need to know these terms, but I wanted to give you an idea of sort of how these different types of energy are extracted. So when you get corn ethanol, you actually use a biochemical process. Okay, so you use organisms to break it down, kind of like it's making alcohol. This is also a biochemical process. And then anaerobic digestion, which is a really important one, we'll go over that as well. Landfill gas and biogas, we'll talk about that, but that's basically these bacteria that break down organic material under conditions of on low oxygen conditions. But again, this entails bacteria, living things actually breaking down this biomass to get the energy out of it. Okay, all right, so let's go over a couple of different types of biomass in a little more detail, and this is all based on your readings. So wood and wood derived, I think pretty self-explanatory. It's basically comes from wood, or any type of wood, whether it's a tree or a brush or leftover tree trimmings from a forest or whatever. Okay, so this is, if you recall, this was about 45% of all of biomass in the U.S. And this is used worldwide as well. But even though the most obvious example would be using a fireplace in your home, actually about 80% is used by industry, electric power, and commercial businesses. So that's actually fireplaces in residential buildings are actually a very minor component of this. But just some examples to kind of help you visualize this. Paper and wood manufacturers are really big because when you make paper or wood products, there's a lot of waste material, and so instead of figuring out somewhere to take it, whether it's to a landfill or whatever, they can actually use that to generate heat and electricity on site, and most of them do, especially paper mills. Paper production is actually a pretty energy intensive process, and they need a lot of heat to process it, so they'll actually use the waste wood that's not used to make the paper to generate heat on site. So that's a really big use of this woody biomass. And then so there are kind of these niche operations where people will generate electricity. Here's, you feel free to click on this, but that's an example of one where you're actually burning wood to generate electricity. Not a major one. But then heating and cooking with wood. This is much bigger worldwide. And this is, our first sustainability note. This is actually a really, really important issue internationally. This is one that a lot of organizations are trying to address. But a lot of sort of non-industrialized, lower-income countries have woody biomass as the main source of not heating homes, but cooking in homes. So there's a couple of really important things here. You can imagine this. Most of this is in Africa, sub-Saharan Africa, Asia, India, it's big. China uses a lot of these cook stoves. But just imagine this woman cooking. Imagine you're in this woman's house. She's cooking, cooking dinner, and this is a stove that's inside of a house. So just imagine this. You notice there's no chimney. There's no way to get the smoke out of the house. Now, of course, there'll be a window open in the house, or there'll be a window up high. But if you know any, I'm sure you're familiar with, burning wood or burning anything. It's going to generate smoke. It's generating carbon dioxide. It's generating carbon monoxide. It's generating particulates. All these really nasty things that you don't want to be breathing in. And this is an extremely common method of cooking in many parts of the world. So you can imagine if, this poor woman that's cooking over the stove, I mean, it's just, the house is just filling with all these toxins and all this smoke. It's very, very bad for her health and for anyone in the house. So indoor pollution from inefficient wood stoves is a huge health hazard worldwide. Again, a major, major problem. A lot of people are looking into this, deriving expensive cook stoves and so forth. But this is a major sustainability problem from, sort of the human, the social perspective. But another really important one is that, even though wood is renewable, we know that, uh, as we have gone over, weeks ago, even though wood is renewable, if it's only renewable if you harvest it at a rate at which it can replenish itself. If you don't, then deforestation can occur, and that is exactly what's occurring all over the world because, if people don't have any other means of cooking or heating their homes, they just go to the local forest. Sometimes it's not local. There are many, many examples of people walking literally hours to go gather some wood for their cooking and heating. But anyway, if they harvest it at a rate that's faster than it can replenish itself, then deforestation results, which is a really big problem for a lot of reasons. Okay, so there's just a couple examples of wood and wood-derived fuel. So here's a really interesting one, waste to energy. So this was in your reading, so feel free to press pause and try to remember what waste to energy means. So waste to energy is a specific term that describes, it's effectively burning garbage. So this is a waste to energy plant in New York. So they really just burn garbage. I mean, it's a little more complex than that, as you hopefully saw in the video. It's a very highly engineered process, but effectively what they're doing is they're taking garbage that would normally get thrown into a landfill and they're burning it, and they're extracting energy out of it. And basically they burn the garbage and they generate steam, which could be used to generate electricity. Maybe they're heating buildings, maybe they're sending it out to local homes with district heating or whatever. But waste to energy, again, this is a specific term. Waste to energy refers to this process where they take waste and they burn it. So you may be wondering, is this, sort of a weird application that very few people do? It's actually in the US, if you look at the municipal solid waste, so municipal solid waste just means household garbage. So this is a breakdown of how municipal solid waste, what happens to it after it's thrown out in the US. So about 54% is discarded. That's a nice way of saying it goes into a landfill. About 35%, this is our recovery rate, so this is basically recycling and composting. But the rest of it is actually combusted and where the energy is extracted. So this almost 12% is actually waste to energy. So imagine that 12% of all household waste in the United States is actually used to generate energy, whether it's heat or electricity. So this is actually a really big deal in the US, about 86 waste energy plants in the US. You have 30 million tons of municipal solid waste a year. I mean, that's a lot of garbage. And it generates about 14 terawatt hours, so 14 trillion watt hours or 14 million kilowatt hours of electricity, which is enough for about over 1 million homes in the US. And of this waste so keep in mind that, if you think of household garbage, not all of it's biomass, right? So a lot of it's, plastic and metal and whatever else people put in there. So about, half of this, waste is actually biomass. So it's actually derived from a living or recently living organism. But that brings us to an interesting sustainability note, which again is another one of these things that I think is kind of surprising to people. So waste energy, this process is generally, I mean, I haven't seen an instance where it's not considered renewable energy. So, you know, burning garbage is considered renewable energy. That kind of begs the question, I mean, is that truly a renewable process? Um, and I ask that because if you think about some of the components that are in household garbage, like metal or plastic, a lot of that is not renewable. So it's just a little bit of food for thought that if you look at renewable energy percentages, if you're accounting for renewable energy in a state or a locality or in the US or even internationally, um, again, I've never seen it not count for renewable energy. So you can burn garbage and count it as renewable energy. So that's a little, a little debatable, but kind of leave it up to you to think about that. So that's waste to energy. Now, anaerobic digestion, this is actually a really interesting one. So anaerobic digestion in general, and we'll go over some specific examples of this in a minute. So in general, anaerobic just means without oxygen, okay? So anaerobic just means without oxygen. And this is an important aspect of this because, so if you think about, like a leaf out on, a leaf falls to the ground out in the open, right? So it's in the forest. So it has access to oxygen, right? There's oxygen in the air, about 20%. So if it's has access to oxygen while it's biodegrading, it's going to basically turn into carbon dioxide. Okay. Now, if you can starve it of oxygen, so you bury it in a landfill or you put it in a big container and you don't allow air to get in there. So if it's digested anaerobically, so digested by bacteria anaerobically, instead of turning into carbon dioxide, it turns into actually about 50% methane. And if you recall, methane is the energy containing component of natural gas. So this is really important. If you can either on purpose or just incidentally starve organic material or biomass of oxygen and allow bacteria to digest it, okay, which happens naturally, then it's actually going to generate about 50% methane, which is effectively natural gas. So if you can capture this, you can use it. So methane can be used for energy, and we'll go over this specific example. And there were a couple of videos detailing this as well. So you can burn it on site. You can burn it at a local power plant. If it's pure enough, you can sort of you pull out any water vapor and other sort of things. You can actually just put it into the natural gas pipelines if you clean it up enough. Okay, so this is really important. Remember, anaerobic means without oxygen. If you can digest this organic material anaerobically, you're going to produce about 50% methane, which then can be used for other things. Okay, so here's two examples. So landfill gas, this is an important term. This is also in your reading, of course. So landfill gas is exactly what it sounds like. It's gas from a landfill. So if organic waste ends up in a landfill, which again, about 50% in the US anyway is organic waste. So imagine, you have this big landfill, and if you have this organic waste that's buried under all this other stuff, if it's buried down there, there's not going to be very much oxygen down there just because it sort of can't come in from the outside. So this waste, any organic material down here, it is going to break down slowly. Bacteria will get down there, they'll do their thing. So whether you want it to or not, all landfills are generating methane because of anaerobic digestion. So all landfills generate methane because of anaerobic digestion. So if they're generating methane anyway, so people figured out, well, let's capture the methane and we can use it. And so basically what you do, this is a cap, you put a impermeable cap over top, and then you provide a means for the sort of get the methane out of there and direct it to whether it's a pipeline or a local power plant or whatever. So as long as you can cap it, prevent the methane from leaking out, which it naturally will do, and then you sort of guide it through a pump to where you want it to go, then you can actually use this. And believe it or not, this is extremely common. A lot of landfills, almost 600 landfills in the United States, and this globally, there's many, many more. But this is really common in the U.S. Where I'm in Delaware, there's one right up the street that uses this technology, and it used to burn in a power plant. I'm not sure. I think it uses it for a local industrial facility now. Anyway, so there's some really interesting sustainability impacts of this. So I want you to sort of think about some of the sustainability impacts. So probably the most important one is that, remember, the landfills they're gonna emit methane. So if we don't capture it and burn it, it's going to leak into to the atmosphere as methane. So just imagine all this methane leaking out into the atmosphere. So if you recall from an earlier lesson, methane is a much more potent greenhouse gas than carbon dioxide. So think about this: if we capture the methane and we burn it, it's going to get converted into carbon dioxide. We're gonna emit all this carbon dioxide, which you would think, well, that's not such a good thing. But the thing is, methane is so much more potent, about 30 times as powerful in terms of global warming potential, or basically it's 30 times as potent as carbon dioxide in terms of warming the climate. So it's actually better that we capture it and burn it and emit CO2 than just let it come out of the landfill. All right, so that's actually a really, really important sustainability implications to this. But also just some sort of other benefits. It does reduce odor because you're capping this landfill, right? So it's not the methane. Methane is odorless, but there's obviously some other odor issues with landfills. So if you cap it, you're actually preventing some of that smell nuisance. It also reduces local ozone, which is another issue. And like I said, in Delaware, we have this Cherry Island landfill, which is near Wilmington, that actually generates about 5,000 cubic feet a minute. So 50 ccfs a minute of methane. That's actually, pretty big. Okay, so the other anaerobic digestion process that's pretty common is, what's usually just called biogas. Okay, so these are controlled anaerobic digestion processes. So here's just an example of one that I was in Denmark a couple years ago, and this was it was a cooperatively owned biogas plant. So there were, I think, 25 local farms that all pitched in basically and bought this plant together. And so what you're seeing, these tanks right here are I think they're called digestion tanks, but basically that's where the organic material goes in. So this is where all the anaerobic process is happening. Okay, so it's a very carefully managed process, so the pH levels and bacteria levels and the mixture of which types of biomass and so forth are very specific. But they mix the organic material in this tank, they get enough bacteria in there, they make sure it's the right temperature and so forth, and basically they generate methane and they capture it, and then for this one, they burn it on site and they use the heat to heat local. They actually have underground hot water pipes that they send to local buildings, and I think they heat all of the local buildings with the waste energy from the generators that they're generating electricity, and they were taking the waste heat and they're using it in the local buildings. So this is really interesting. We were in this a small farm, and this was actually a family-owned facility, and they had an issue, a big fire as it turned out, and they were building a new anaerobic digester. So this is actually a view from inside of a tank. So you can see, this guy's about 6 feet tall. This is a huge tank, probably 40 feet tall. You can see this propeller thing here. That's actually to mix the biomass sort of slurry that happens. So you want to make sure you keep mixing it to get the digestion going. But this is the inside of a tank, and then this was also, this is a local farmer that took all the organic waste from the local farms, actually from the local restaurants and grocery stores. And then, so an interesting sustainability application of this, and this is pretty common for these types of facilities, is that imagine you put all this organic material, okay, that's otherwise wasted, right? So instead of putting it in a landfill or whatever, you're taking it and you're putting it in your digester, okay? Then you process it without the oxygen. The methane is captured, okay? So this is really good. Methane is captured, we use it. What's interesting is that so there's any water, so any biomass generally is going to have a pretty high water content, so they'll capture the water, it's actually purified and it can be reused. What I think is really interesting is that there's solid organic material that's left over that's not digested, okay? So not all of it gets converted to methane, so some of it is a leftover sort of solid material, and you can use that as natural fertilizer. And so both of these examples, both of these farms, they would actually take that leftover solid material, it's really good natural fertilizer, and they would provide it back to the farmers, and then they sort of put it back on the farm field, and then it kind of, you can imagine sort of closing that loop. You take what's left over from the biodigester, you apply it to the farms, and then you use that to feed the whole process again. Okay, so that's just a pretty interesting application, and this is all common, in the U.S. and worldwide. Very important means of using bioenergy. Okay, so real quick note on ethanol. So ethanol is basically just alcohol made from sugars. Without getting into too much detail, in the United States, it's almost entirely corn. You've probably heard of corn-based ethanol. In Brazil, just one note about an international application is sugarcane is a huge source in Brazil. Almost all cars in Brazil are actually designed to run on up to 100% sugarcane ethanol. There are some other means, again, like I said earlier, we're trying to figure out ways to use things other than corn, switchgrass, wood chips, these are all lignocellulose based. But the problem is, again, lignocellulose, if you recall, is very hard to break down, so it requires a lot of energy to do it. We haven't found a way to really make it energy positive. So, in the US, this is pretty much all used to add to gasoline. And this is because there is the Renewable Fuel Standard, which is part of the, I forget, the Energy Act, a major piece of federal legislation in 2005 actually mandates, so it has to be added to gasoline. And there's actually, there's amounts that they mandate, so this renewable fuel standard is they have to add so many billions of gallons of ethanol in the US. So that's a story for another day, but whether or not that's sustainable or a smart policy is very controversial in the US. And then just another quick note, if you've ever seen these terms, E10 just means 10% ethanol, E15 is 15% ethanol, so you'll see this on gasoline, if you go to a gas station to fuel up, it'll probably say E10. All gasoline is at least E10. Now, if you've heard of flexible vehicles, they can use up to E85, which means 85% ethanol. Just a side note, ethanol, one of the reasons people don't like it is because it's actually really tough on engines, especially small engines like lawnmowers and so forth, outboard motors on boats. So not all, you can't just make ethanol and expect, to be 100% ethanol and work in all engines. It's only certain types can use high percentages of ethanol. Okay, last source, we have biodiesel. So ethanol is basically made from starches, whereas biodiesel is made from oil, animal or vegetable oil, so waste oil, soybeans, algae, jatropha, canola oil. So just, the easiest thing to remember is that ethanol is made from starches, food, basically, edible food anyway, whereas biodiesel is made from oil. So this is a food product, but it's not really something you'd eat, per se. So there was an interesting video on showing how a woman made biodiesel at home, and it is not that complicated a process if you just have the right materials to make it. This is a very minor, if you recall, I think it was over like 99%, something like that, 98% of the biofuel in the US was ethanol. So I'm not really going to go over Eutropha. There was a video on that, but that's an interesting application. Okay, so very last slide. Sustainability issue. This is a major issue in the US, especially, but it's because it's not as big of an issue worldwide, or corn is not used as much worldwide. Major issue in the US. So the main food crop that's used to make ethanol in the US is corn, really big deal. So maybe think about a couple of problems, and this was in your reading. So it can, we're using food for fuel. So, you know, if you kind of mix these two markets together. So we have, our market for energy or our fuel, and then we have our food market. You kind of start mixing those two together. It can get a little bit messy. It can increase prices. Sometimes it can decrease, but um, there are some case studies of, where the price of corn has gone up enough that it's caused major problems for people. Um, but I think a really huge issue, and this was addressed in your reading, is that, if we're growing crops specifically to make energy out of them, this is an issue because farmland, while we have enough worldwide, I mean, especially in other parts of the world, it's a problem that we're using up valuable farmland. So, as population increases and we start losing more and more topsoil and so forth, and if we're growing crops specifically for energy, maybe we should consider using that for food since, we do have food issues worldwide. Um, and also, this is a problem more internationally than anything else, where you're taking, sort of these native crops, or, there's like they're cutting down rainforests in Brazil to grow things like soybeans. If you are compromising the sort of integrity of the local natural environment for fuel, again, yes, energy is important, fuel is important, but if you look at, the balancing the two, it's probably, maybe better to find other ways to use energy. Now, if you're using um, land that's not otherwise being used for, food, or it's, if it's just sort of this marginal land that nothing else can grow on, and you can grow energy crops on that, then I say more power to you. Because if you can use that, like if you watch that Eutropha video, they can grow Eutropha and it'll actually sort of replenish the soil, and you can use it for energy. So there's no really simple solution here. Energy is important, food's important, land's important, native crops and biodiversity is important. So these are just some of the issues that pop up when we're dealing with energy and biofuel. Okay, and that's it for this presentation.